The next unit we're going to talk about deals with two main functions, the exponential and logarithmic function. But before we can get to that, we need to talk about inverse functions. So we're going to go first through this property that's known as one-to-one, so some functions can have it. Then we're going to talk about the horizontal line test, and then we can actually define what is an inverse function. Okay? So when we say a function is one-to-one, it means that no two elements in the domain correspond to the same element of the range. So essentially the way you can kind of think of this, if your x values are different, then your y values have to be different. So when we started talking about whether something was a function or not, we were checking that the x's didn't repeat. We didn't care what happened to the y's. Now we want to kind of take it a step further and say, do my y values repeat? If they do, then my function is not one-to-one. So let's take a look just at two tables. These would correspond to different pairs on a graph. And we want to determine whether these functions are one-to-one. So looking at the first piece, none of my x values repeat, so this is definitely a function. But here, because two different x values give us the same y value, this function is not one-to-one. So a lot of times we'll also just write 1 with a -1 instead of writing the full phrase out. So when the y repeats, it's not one-to-one. On the second example, however, if you take a look at all of these different x values, it's definitely a function because my x values don't repeat, but also all of my y values are unique. So since there's no repetition, this function is one-to-one. Okay? So this is a property we want some functions to have to be able to define an inverse. So let's try this now with a graph. If you remember our basic shapes, this is our absolute value function. And the problem with this is, if I pick this y value here, there's two different x values that give us this same output. So this is the first x value, this is the second x value. So unfortunately, two input values give us the same output. This function is not one-to-one. Okay? So this concept is actually something that's known as our horizontal line test. So we had the vertical line test to determine if something was a function or not. Now we have the horizontal line test to determine if that function is one-to-one. And so it's very similar to the vertical line test. If you can draw a horizontal line and it hits the graph in multiple spots, your function is not one-to-one. If I can't do that and every vertical line hits the graph in just one spot or not at all, then it is one-to-one. So let's take a look at two different examples. For this first example, no matter how I draw a horizontal line, it's only hitting this graph in one spot every single time. So this does pass the horizontal line test, and this is one-to-one. However, for the second example, I can draw one line right here, and immediately this horizontal line hits in two spots. This one is not one-to-one, okay? So we need this property to happen for an inverse function to exist. And when we talk about an inverse function, the idea is it's kind of undoing the process and landing you back to where you started with. So thinking of like square and square root, we know those two cancel each other out. Same thing if I take the cube root of something cubed, it cancels out. These operations undo each other. In the same way that addition and subtraction are considered inverses of each other. And same thing with multiplication and division. They undo the process. So that is what an inverse function does. We use this notation with a -1 attached to f to indicate that it's the inverse of f. The one thing you have to be really cautious with is this is a notation. It's not treated like an exponent. So it does not mean put this thing in the denominator. It means this is the inverse function. Okay? So I want to give you a little picture just kind of as to what I'm talking about here of how it's undoing this process. So typically we're used to starting with our x values. So here is our domain for our function f. Okay? Then when I plug this into my function, I'm getting output values, which are y values. Okay? So this would correspond to the range of our function f. For the inverse, I'm going to switch these roles and reverse the process. So I'm really going to land right back to where we start for the inverse function. So what was the range of the function becomes the domain of the inverse. And likewise, now what was my domain becomes my range for the inverse. So these roles are switching to undo this process. Okay? So I'm going to show you why we need this property of a function to be one-to-one to be able to have an inverse. So from our very first example, we know this function is not one-to-one because these y values repeat here. If I were to go try to graph the inverse, what would happen is here's our x and y's. These roles would flip-flop. So I'd have 4, 4, 8 as my input and 0, 1, and 2. And now I run into a problem because my input repeats. So the result is something that is not a function. Okay. And that's a problem. I don't want that to happen. But if I do have something that's one-to-one, like in that second example, when I go to find the inverse, I switch the roles of x and y. So my input is now 4, 6, and 8, and my output is 0, 1, and 2. And here I have no issues. My x values are unique. So the result here is a function. And that's what I want. That's why we need this property of one-to-one for the inverse function to exist. So let's take a look at some properties now to kind of summarize everything that we had. So first and foremost, the domain or the input of our function becomes the range for the inverse because x and y's are flip-flopping. And then likewise, the range of my function is the domain of my inverse. Okay? Because these operations also undo each other, when I evaluate one at the other, it's going to cancel and land you back with x. And same thing when I flip-flop which one I evaluate in the other, it cancels and lands you back to x. So if you have two one-to-one functions that do this, they are inverses of each other. So just to give you kind of a quick example, like if I take the cube root of x cubed, it lands me at x. And likewise, if I cube the cube root, they cancel each other out and land at x. So x cubed and the cube root of x are inverses of each other. Okay? Now the thing that happens with their graphs, because x and y are switching roles, all of their coordinates are switching roles. So I'm actually going to go through the fifth one first. If you have AB on your graph of the function, x and y switch, so BA is going to be on the graph of the inverse. And what results is that these graphs end up being reflections about the line y equals x. So let's look at this with an example just to kind of verify. We have two functions and we want to show that they're one-to-one. And then we want to verify that these two functions are inverses of each other. So the problem is right here, I've got this square function that definitely fails the horizontal line test. However, we do have a restriction here, and this restriction is going to be nice because it's going to make sure that we do pass our horizontal line test. So I'm going to go ahead and I'm going to first, I've got to show they're one-to-one. So I want to figure out what the graph of each of these looks like. So we're going to graph f of x, and then we're also going to graph g of x. So this is 2 minus x, which is the same thing as negative x plus 2, just so I can see the transformations. Okay. So for this first one, we've already spent a ton of time going through graphs of parabolas. This minus attached to the x squared means it's opening down. and that 2 means it's moving up 2. So the graph is going to go through to 0, and it's going to be facing down like this, okay? But because we have this domain restriction that our x has to be greater than or equal to 0, we get to completely ignore everything on this half of the graph. So really that piece is completely gone. So as a result, this function does pass the horizontal line test, and this is 1-to-1 now. Okay. When we go to graph our square root function, we technically have 2 transformations that are in here. So the very first one is this +2, which means we move to the left 2. And then we also have this minus sign attached to the x, which means we reflect over the y-axis. And the order does matter for these. So the very first thing I have to do is my horizontal shift. So I would move that to the left 2, and my graph would look like this. But then I need to reflect it, that's technically -2, over the y-axis. And so this point here would actually flip over to 2, 0 and be going backwards. Okay? So this is the graph of the function g of x. Right? And then just to give you insight, if we go ahead and merge these to the same graph, of course my scale, oh, it's not even going to work nicely. My scale is a little bit off. If I were to go, let's see if I can make this happen nicely. If I were to plot this point up here at 2, 0, and then it would come down, these graphs are reflections about the line y equals x. So you could fold it along this line and you have the same thing on each half of that paper, okay? But this one also definitely passes the horizontal line test, so this is 1-to-1. So now that they are 1-to-1, we want to go ahead and verify that they are inverses. So I need to take f, and I need to evaluate it at g of x. And then I need to do the same thing in the other way. I need to take g, and I need to plug in f of x. So we're doing that composition of these 2 functions. So what this means is I'm taking f and I'm evaluating it at this expression for g. So anywhere I see an x in my expression for f, it's going to get replaced by this square root. So we get 2 minus x squared, which means we get 2 minus this square root squared. Okay? And then our square and square root cancel. So this is 2 minus x. Distributing that minus sign, it's 2 minus 2 plus x. And those 2's cancel each other out, and that just ends up equaling x. Okay? So it happened in one of the directions. Now hopefully it happens for the other as well. Here now I'm going to take my function g and I'm going to plug in this expression for f. So anywhere I see an x in g, it's going to get replaced by 2 minus x squared. So this becomes the square root of 2 minus x squared. And then distributing that minus sign gives us 2 minus 2 plus x squared, which means take the square root of x squared. And then technically here you get an absolute value because the square root has to be something that's positive. But however, our x is greater than or equal to 0. So we do end up with just x, okay? But that's exactly what we want. So both of these functions unravel each other and just land us back to x. So yes, these functions are inverses. Okay. All right. So now what do we do if I just give you an expression for my function f? How can I possibly go about finding the expression for the inverse? Okay. And this is where we use this definition to do that. So the very first thing we do is this f of x just means the y values equal this expression. So I'm going to replace this f of x with y. Then my roles are flip-flopping. So every x is going to turn into a y, and every y turns into an x. So you're interchanging all the variables. Then you want to solve for y, and this is going to be our inverse function. Forgot that minus sign attached here. Okay. So let's try an example. We're told this function is 1-to-1. We don't have to go about solving or showing that it is. I want to find its inverse, and then I want to find the domain and range of each of them. So very first thing I'm going to do is I'm going to find the inverse function. Okay. So immediately I switch that f of x to y. This is the same thing as saying y is equal to 7 over x plus 2. And now I got to switch these roles. So this y turns into an x, and over here this x turns into a y. And now I need to solve for y because I need to get a function that's y in terms of x. So you have a couple different ways you can approach this, but the easiest thing, I'm solving for y and it's in the bottom. So let's go ahead and multiply by y plus 2. And then I'm going to do the same thing over here because then at least these two cancel. And this gives us x times y plus 2 is equal to 7. At this point, your gut might tell you, oh, let's distribute everything. Absolutely, you can do that. You'll get a slightly different expression. But something that might be a little bit easier is we could just divide by x at this point, because that will make this cancel. And then on the left, we're just left with y plus 2, and that equals 7 over x. And now we're almost there. We just need to subtract the 2. And so our y is 7 over x minus 2. You can condense it to a single fraction if you want, but you don't need to. You can leave it just like this. But now that I've put it in that correct function form, this is the inverse function. Okay? So the inverse of 7 over x plus 2 is 7 divided by x minus 2. Okay? Now what we can do is we can actually use both of these to our advantages. So here is our function, 7 over x plus 2. And here is the inverse, 7 divided by x minus 2. I know finding ranges is pretty difficult, but what we can do is instead find the domain of each of these, because we're definitely much better at finding domains than ranges. So for this first function, we run into a bit of a problem when x is negative 2. So that value has to be excluded from our domain. So in interval notation, the domain would be negative infinity to negative 2, union negative 2 to positive infinity. For this function, 0 poses a problem. So I know my x cannot equal 0. So in interval notation, that would be negative infinity to 0, and then 0 to infinity. Okay? So the domain's much more straightforward to find because that is what we're accustomed to. We know what values cause us issues. And so I can actually just use that to get the range. So the domain of my inverse becomes the range of my function. And vice versa, the domain of my function is the range of the inverse. So the range of 7 over x plus 2 is negative infinity to 0, 0 to infinity. And then the range of the inverse is negative infinity and negative 2, union negative 2 to positive infinity.